Hi everyone, I am Marina. I'm a current PhD student at PUC-Rio, and I work as a researcher at the Laboratory of Applied Mathematical Programming and Statistics, also at PUC-Rio. Today we present the work entitled A Novel Semi-Parametric Structural Model for Electricity Fault Curves, developed with some of my colleagues that also participated during this study. So our main goal is the definition of a semi-parametric structural model for electricity swap prices, where we define its dynamics by the underlying elementary prices, which are in our context, unobserved daily prices or contracts that composes the original swaps. So we can understand them as smaller pieces of the swaps traded in the power market. As a result, we have a forward curve that has no overlapped structure, since these elementary contracts all have the same duration, which is a day, and we calculate them by a hierarchical estimation procedure that acknowledges the arbitrage opportunities in the power market. So the main assumption that governs our structural model is the non-arbitrage argument, which is the most important principle in any financial model. So as I've just said, elementary contracts are smaller pieces of the swaps traded in the market. So we would expect that in a competitive environment, a swap defined by a continuous delivery period should be equivalent to trade multiple elementary contracts for the same interval of time, meaning that arbitrage opportunity should not exist. So equation 1 defines the net present value of arbitrage, here represented by delta Ti, where T is a trading date and I is a swap traded on that day defined by its delivery period. So the capital FTI is the swap price we observe in the market. The small ftj is the elementary price we want to estimate for the maturity j, and R is the discount rate. The interval here in the summation actually defines the delivery period of the swap price, where HTI is its time to maturity, and the delta capital TTI is its duration, both defined in days. As I said, we would hope that delta Ti would be zero on a competitive market, but that is completely unrealistic. Actually, studies that apply smoothing techniques to obtain those elementary prices, they usually disregard overlaps in order to obtain feasible solutions. But in our case, we actually acknowledge their existence and use them as an important source of information. And we do that by adding this error term here, this delta Ti, on the expression of the swap prices. And we see here by the equation 2 that the swap prices are just a sum between a portfolio of elementary contracts for its delivery period, plus this error term that has the interesting interpretation of being the arbitrage level for the trading day T and swap I. In order for us to have our structural model defined on a state space scheme, we now must define an equation for the elementary prices, which are our state variables. And we do that by equation 4. So in equation 4, we write the elementary price on date T and maturity J as a sum of a parametric and non-parametric part. So this equation actually gives the name semi-parametric of our model. In this first term, we can add any structure we want to impose on elementary prices. That can be seasonality or any exogenous variable we think that drive its dynamics. And this residual, we actually do not consider any parametric representation for them. We just assume that they are the smoothest function between a set of smooth functions. One thing we must highlight here is that these error terms are not the usual uncorrelated errors of state space models. So with our structural model in hands, we now define a hierarchical procedure to estimate the elementary prices. In the first step of this procedure, we compute a new data set composed of arbitrage-free prices. And what are those arbitrage-free prices? If you recall the expression of our observation variable, which are the swap prices, we will see that the arbitrage-free prices are just the weighted average of the elementary contracts. So manipulating this equation, we can write them actually as the difference between the swap prices and the arbitrage levels zeta Ti. Using that equation, we calculate those arbitrage-free prices by solving an optimization problem for each trading day, in which we minimize the infinite norm of the arbitrage levels for the day on an iterative manner. One thing here is that this stage actually can be used to detect outliers, since if we find contracts that have a high arbitrage level associated with them, we can argue that its behavior diverges too much from the average, and we might disregard them for the next steps. In the next stage, we estimate the parametric part of our model, which is basically the calculation of the vector of coefficient beta. And here we define a reduced form model by replacing the dynamics of elementary prices on the equation of arbitrage-free prices that I've just mentioned. With this closed form in hand, we can actually estimate the vector beta by ordinary least squares. And in the final stage of our procedure, we estimate the residuals applying the maximum smoothness criteria following Bentico-Quebec 2008. But here we have two differences when compared to the usual literature. First, as I said, we do not assume any parametric representation for the residuals. And also we add a second objective, which is the maximum smoothness criteria on the time dimension, in addition to the maturity dimension, which is the usual approach in the literature. And we do that because, as we will see next in our case studies, this is really important when we deal with scarce data set from low liquidity markets such as Brazil. In order to highlight the contributions of our work, we consider the traded assets of two contrasting power markets. In one hand, we have Nord Pool, which is a consolidated power market. And in the other hand, we have the data set from Brazil, represented here by the BCE, which is a really incipient power market with low liquidity. So scarce data is a reality. For example, for the monthly contract to be delivered 6 months from now, we have 93.6% of missing prices. So our approach here will be really useful, as we're gonna see next. Before showing any results, we must first define the structure we want to impose on elementary contracts. And for now, we are just addressing seasonality through a truncated Fourier series with only one harmonic. And equation 5 translates the final dynamic of the elementary prices. And for simplification purposes, we consider the discount rate equal to 0. As I said, on the last stage of our estimation, we apply the maximum smoothness criteria both in time and maturity. But since the Nordic dataset doesn't have an issue regarding missing data, we apply just the maximum smoothness in the maturity dimension for the set, while the time dependency was also added for the Brazilian dataset to address the missing prices. In this case, we must define the weights of the objective functions, represented here by lambda 1 and lambda 2. For now, we consider that they were equal to 0.5 divided by their correspondent objective function, which can be or the maximum smoothness in time or in the maturity. And we do that to maintain the objective values on the same scale. To exemplify how the objective formulation can impact on the estimation procedure, we analyze the trading date May 2nd of 2018 from the BCE, where only the N+1 swap was traded. So on the left, I show the residuals obtained just by smoothing them in the maturity dimension. And on the right, I have the residuals applying the maximum smoothness both in time and maturity dimension. On the left, we can see that the optimal solution is just maintaining the final slope of the residuals that compose the traded swap, since the maximum smoothness criteria is basically the minimization of the second order derivative. But when we consider the time dependency here, we have a more complex dynamic, since we now consider information from trading dates close to each other to address the scarcity of data. Another way we can see the impact of this approach is by looking at the recovered arbitrage-free prices. So on equation 6, I show our reduced form model, where YTI is the arbitrage-free prices. The capital XTI is just a weighted average of the structure imposed on elementary prices, and net TI is a weighted average of the residuals of elementary contracts. So this equation translates how the structure imposed on elementary prices is reflected on arbitrage-free prices. So since this is a constant after the estimation procedure, We can replace here the residuals obtained or with the maximum smoothness and maturity or using the time dependency. And we can recover any arbitrage-free price we want for all trading dates and swaps. So we do that here, looking for the M+6 time series from Brazil, which have a high amount of missing prices. On the left, I show the recovered prices using only the maximum smoothness and maturity, and on the right, adding the time dependency. We can see in the left that this result implies on a really noisy structure, while on the right, we have a much more coherent time series with much less noise. Another impressive result we obtain with our model refers to the dimensionality reduction through PCA. In previous studies, the authors found that they needed more than 10 components to explain 95% of the variance of a data set composed by prices recovered as a combination of the elementary prices. In the context of our study, we decompose the matrix of the residuals instead, and to evaluate this approach, we look at the number of components necessary to explain a high percentage of the variance of the residuals, and also the interpretability of factor loadings. One thing that must be highlighted here is that we performed PCA on a truncated data set composed by the residuals that were based both on the maximum smoothness and based on some arbitrage-free price. So we don't have any issue regarding extrapolation. So for the Brazilian data set, we found 3 components to explain 98.4% of total residual variance, and we found the traditional level, slope, and curvature shapes. For the Nord Pool data set, we also found 3 components, but to explain 97.4% of total residual variance. We also found traditional level and slope shapes for the first 2 factors, but the third still maintains a seasonal pattern. We believe this impressive result when compared to the literature is mainly due to the fact that we are applying PCA on the residuals instead of elementary prices or any data set composed by a combination of elementary prices. Actually, with this result, we can perform a probabilistic forecasting of the arbitrage-free prices. First, as I said, we perform PCA under a truncated data set. So we must define some parametric representation for the factor loadings in order for us to obtain those weights that are the factor loadings for any maturity J we want. We might be interested in forecast. Then we can generate scenarios for the components, since it is a much smaller number of time series to be modeled with a characteristic of being orthogonal to each other. So we can use univariate models to forecast them. Then we can generate the scenarios for the components, and using the expression of PCA, where we write the residuals as a linear combination of the components, we can obtain the scenarios for the residuals and then the scenarios for the arbitrage-free prices by using our reduced form model. That's pretty much it. Thank you, everyone.